Previously, we talked about capacitors in AC circuits and inductors in AC circuits and what happens when we mix capacitors and inductors in AC circuits. And we saw that a capacitor tends to block low frequencies. In fact, it'll block DC, but it tends to pass high frequencies. Inductors tend to block high frequencies but pass low frequencies. And if we put them together in series, we find that capacitor and inductor in series will pretty much look like a short circuit at a particular frequency we call the resonant frequency. But above that frequency, it's going to have a high impedance, and below that frequency, it'll also have a high impedance. So the impedance of an inductor and capacitor in series will tend to go down at a particular frequency, the resonant frequency, and then go back up. But if we put them in parallel, we get the opposite effect. We tend to get a high impedance at the resonant frequency where the capacitive reactance and inductive reactance are equal, and that starts low and goes high at that resonant frequency and goes back down. So this is going to be an inductor and a capacitor in parallel, and this will tend to be an inductor and a capacitor in series. So we get these two curves that tend to react to one frequency. Well, we could pass information from one circuit to another, but using a inductor and capacitor in series, we could let certain frequencies pass from one circuit to another, but not those above and below. Or using the capacitor and inductor in parallel, we could have a circuit that passes frequencies from one circuit to another, but allows frequencies near the resonant frequency through, but does not allow frequencies above and below the resonant frequency. And we talked about some of the other characteristics, like if we add resistance, it's going to change the response of that. So in the parallel circuit, it'll lower that peak and broaden the range of frequencies that tend to pass, and the series circuit will tend to do the opposite. And we remember that our actual impedance will be equal to our resistor if we have resistance in there. But what we're going to look at today is how we can manipulate this to create electronic filters. Now, what does a filter do? It allows some things through and blocks others. We can have filters that filter out particles, let liquids through and stop particles, or stop particles bigger than a certain size. We can have filters for light that let certain colors through but block other colors. And electronic filters will let certain frequencies through but block others. So let's take a look at different kinds of electronic filters. And let's use as an example some place we might want to have a filter, which is in an audio amplifier system. So if we want a speaker system, it's very hard to make a speaker that can respond well to the entire audio range of frequencies. To respond to the low frequencies, we need something with a large cone that can move a lot of air, but doesn't need to move it fast. For higher frequencies, we need a small cone that can move quickly, but doesn't really need to move a lot of air, because the energy is placed a little bit differently along that curve. So higher frequencies, we can get a lot more sound with less energy. So we don't need to move a lot of air, but we need to move it fast. Low frequencies, we need to move a lot of air, but we don't need to move it fast. So we make woofers that are big and move a lot of air. And then we make tweeters that are small and move a little bit of air very quickly. So when we have the output from the audio amplifier, we want to go, well, here's our tweeter, a little speaker, and here's our woofer, a bigger speaker. And we want to send our low frequencies to the woofer because it's not going to respond well to high frequencies, it's just going to produce heat. And likewise, the tweeters, we don't want to send low frequencies there because they're going to do the same thing. It's not going to respond well, it's just going to produce heat. So we want to take the high frequencies to the tweeter and the low frequencies to the woofer. And this is not really a practical way to do it, but it'll get us started at looking at how these circuits can work. What I'm going to do is have a circuit that's a resistor and a capacitor in series. Let's take another look at this real quickly before we move on to the speakers. I'm going to draw that a little bit bigger. And let's recall some of the things we know about capacitors and resistors and series circuits. Let's let this go back to a alternating current source. Let's say it's 10 volts. Let's not worry about the frequency at this point. And how are these going to react? Let's put some voltmeters across here. And what do we know? At low frequencies, this capacitor is going to look like an open circuit. It's going to have a high impedance. In fact, at DC, it will look like an open circuit. As we start to go up in frequency, it's going to have less and less capacitive reactance and look more and more like a low impedance. So at low frequencies, high resistance leads to high voltage. So low frequencies, we're going to get high voltage. The resistor, on the other hand, is going to react to all frequencies equally. But what's going to happen, seeing that they're in series? We have to take into account how series circuits work. And according to Kirchhoff's voltage law, we do know that the voltage across this component and the voltage across this component must always equal the source voltage. So low frequencies, we get high voltage. What happens at high frequencies? High frequencies, we get low voltage. So that voltage is going to change as our frequency increases. So let's say just make a little graph here. Here's our frequencies. And let's say this is at 20 hertz, the threshold of hearing. And let's put in the middle 1 kilohertz and up here 20 kilohertz. And let's say at 20 hertz, we have, let's say 9 volts across here. It's almost the full 10 volts. So 20 hertz, we get 9 volts here. What voltage are we going to get here? We're going to get 1 volt. So at the low frequency, we get a pretty high voltage across the capacitor, but the voltage across the resistor is going to be pretty low. Now let's crank that up to 1 kilohertz. And let's just say that at 1 kilohertz, we get 5 volts across the capacitor. Well, if we have 5 volts across the capacitor, what are we going to get across the resistor? We're going to get the same voltage because 5 plus 5 equals 10. So right at 1 kilohertz, we're going to get our capacitor voltage is going to drop down to 5 volts. Our resistance voltage is going to climb up to 5 volts. Now let's go up to 20 kilohertz. And let's say at 20 kilohertz we have only 1 volt across the capacitor, which is going to leave us with 9 volts across the resistor. So that's going to climb up. That's going to go, oops, there we go. That's going to go down. And so we see that the resistor is going to have a high voltage at the high frequencies, but the capacitor is going to have a high voltage at the low frequencies. So I just put HF there and LF here to remind us that creates voltage at high frequencies, that creates voltage at low frequencies. And let's just see what we can do with that. We can now, let's see, we want the high frequencies to the tweeter. So we can put the tweeter here and the woofer, much bigger speaker, down here. So we have just created a crossover to divert high frequencies to the tweeter and low frequencies to the woofer. Now this isn't really a practical circuit for a crossover because we have a resistor in there and current through resistors produces heat that's going to waste energy, but it gives us an idea of what we can do with a resistor and a capacitor to give us different frequencies. But we can use this in the low current areas such as the beginning stages of an amplifier to filter there. So instead of running that straight to the speakers, we can create a filter that will, let's say we want to block high frequencies. Well, this is going to have its highest voltage at low frequencies. So we can make a filter that only passes low frequencies, a low pass filter, by putting our next circuit, whatever that is, across that capacitor. Now normally we would draw a low pass filter a little differently, so let me redraw this. Doesn't change the circuit any, just changes the way we look at it. So we're going to have our resistor there, our capacitor there, and our output to our next circuit right there. So now we have a low pass filter. All we have to do is calculate what frequencies this is going to work at. So notice that the low-pass filter, if we're using just a capacitor and a resistor, that our capacitor is going to be in parallel with the signal. So the signal is going this direction, and the capacitor is in parallel with that signal. And we can think of it this way. Remember that high frequencies go through a capacitor. So if high frequencies are being shunted away, that means it's the low frequencies that make it to our circuit. So capacitor across the signal, we have a low-pass filter. Now let's just flip those. Now, remember that to get the higher voltage at higher frequencies across here, another way to look at it is through the capacitor. Remember, high frequencies go through the capacitor, and so they go on through, and so that's going to be a high-pass filter. So high frequencies through a capacitor. I could redraw it here. Maybe that'll make a little more sense, although it doesn't change the way the circuit works. Just helps us with our little memory aid here. High frequencies go through the capacitor, and so if we have the capacitor in series with the signal, we get a high-pass filter. So that is the basics of an RC filter. So we just made an RC filter. And the arrangement is, once again, if the signal goes through the capacitor, we get a high-pass filter. But if the capacitor is across the signal path, we get a low-pass filter. Because once again, the high frequencies will go through the capacitor. So if the capacitor is here, they go through it that way. But if the capacitor is there, they go through it that way. So high-pass filter if the capacitor is there. Low-pass filter if the capacitor is there. Now, how do we calculate which frequencies go where? That's fairly simple, because as we already saw, let me draw our chart here again, our little graph. Our capacitor voltage starts high and goes low as our frequency goes up. Our resistor voltage starts low and goes high, and somewhere they're going to cross. And that crossing point is called the cutoff frequency. Or actually, we should write that as, well, got our F there already. That frequency is the cutoff frequency, F sub CO. So how do we calculate that? Well, we talked about calculating the resonant frequency before, and it's very similar here. So the cutoff frequency is the frequency where the impedance of the capacitor, the capacitive reactance, equals the resistor, and then they have the same voltage, right? Remember, take a quick look at this so we don't forget how this works. It's a series circuit, and so if this has 5 volts and this has 5 volts, well, they must have the same impedance. Let's say this is 100 ohms. Well, if that is 100 ohms with 5 volts across it, and this also has 5 volts, what's that tell us? This must also be 100 ohms. So we were looking at our graph, and we saw that at 1 kilohertz, we had equal voltage. Therefore, at 1 kilohertz, we must have 100 ohms here. I'm not going to do the calculations. We've done that before. But we see that at that frequency, we have 100 ohms of capacitive reactance here, 100 ohms of resistance here, equal impedance. Therefore, they have equal voltage. And so the cutoff frequency is the frequency where those voltages are equal or the impedance is equal. So our cutoff frequency is going to be the frequency where our resistance equals our capacitive reactance. And what is the frequency for capacitive reactance? So capacitive reactance is 1 over 2 pi fc. So the cutoff frequency is where 1 over 2 pi fc equals our resistance. So we just do a little algebra trick. We can swap terms around like this, move our frequency over here, and put our resistance over there. So just like that, we just swapped it out. That's going to be our cutoff frequency. So our cutoff frequency is equal to 1 over 2 pi RC, and we work that formula just like the capacitive reactance. But instead of telling us the capacitive reactance, we swap out those two terms, and now 1 over 2 pi RC tells us the cutoff frequency for that particular filter. And whether it's a high-pass filter or a low-pass filter depends on where we arrange the resistor and the capacitor. So, what's the next thing we need to know about that? Let's draw a graph of frequency response. And if we make this a logarithmic graph, trying to make it look sort of logarithmic here, we're going to get a graph as our frequency goes up, where the response of the filter, the voltage across the capacitor or the resistor, if you will, is going to be pretty steady until we hit that cutoff frequency, and then it's going to drop off. This will appear to be a straight line because of the logarithmic nature of the scales, and so it's going to drop off at a certain rate. And the point where the resistance equals the capacitive reactance, depending on whether it's a high-pass filter or a low-pass filter, this is obviously a low-pass filter. So the cutoff frequency is going to be where this drops off to 3 decibels below. So we're looking at power here. When it drops down to the 1/2 power point, remember when we are at that cutoff frequency, we have half of our power on one component, the other half of the power on the other component. So the cutoff frequency will be where the power is 50-50 between the components. So if we look at the power across the, in this case, low-pass filter, it's going to be the power across the capacitor. We're going to see that our cutoff frequency, our power being passed, is going to be 3 decibels below the peak. And so that is going to be what happens at the cutoff frequency, is the 3 dB point. So that's by definition where the cutoff frequency is, where the power transfer drops down by 3 decibels or 50%. Remember, decibels, we talked about that much earlier. When we have a 2-to-1 ratio in decibels, that's 3 decibels. If we double something, that's 3 decibels. If we cut it in half, it's 3 decibels. So if the power coming in is 100 watts and the power going out is 50 watts, that's 50%, that's 3 decibels. So that's how we define that cutoff point. Now if it's a high-pass filter, we just flip the capacitor and the resistor, and we're going to get something that looks more like that. And once again, the cutoff frequency is where, so the response comes up and up and up, and when we are 3 dB below the peak, we are at the half power point, and that is the cutoff frequency again. So that's how we define the parameters of an RC filter. The cutoff frequency is where the voltage across the component that's making the output is 3 dB below the max, and whether it's a low-pass filter or a high-pass filter is simply the orientation. If the capacitor, once again, let me redraw this real quickly. Here's our AC source. So if our capacitor is in line or in series with the signal, that's going to be, remember, high frequencies go through the capacitor, so that's a high-pass filter. But if we flip this around and put the capacitor across the circuit, high frequencies go through the capacitor, so they're shunted away, so this now makes a low-pass filter. And then once again, as we just discussed, the cutoff frequency is where the capacitive reactance equals the resistance, and that's calculated with cutoff frequency equals 1 over 2 pi RC. Now, what about an inductor? Well, everything works about the same. I don't need to say too much about it, except an inductor, remember, inductors tend to block high frequencies and allow low frequencies. So let's make that circuit with an inductor. Let's put our resistor here, our inductor here. So the inductor is now parallel to the signal. The signal is going across the inductor. The inductor likes to pass what? High frequencies or low frequencies? Low frequencies go through the inductor. So if the low frequencies are being shunted down, the high frequencies go there. And if we swap these around, now high frequencies are blocked, so low frequencies go through the inductor. High frequencies, therefore, are shunted away. So if our signal goes through the inductor, it's a low-pass filter. If the signal goes parallel to the inductor or shunted by the inductor, that makes it a high-pass filter. So let me just draw the both so we can kind of compare them and see how they are in our minds. So here's circuit number 1. So what is that? High frequencies go through the capacitor, so that's a high-pass filter. Now let's draw the same thing down here, except getting sloppier by the moment, aren't I? Okay, so now the low frequencies go through the capacitor. So now the high frequencies go through the capacitor and are shunted away. High frequencies, therefore what's left is low frequencies. So this is a low-pass filter. Let's do the same thing with an inductor. Let's put the inductor in series here with the resistor there. Okay, what do we know? Low frequencies are going to go through the inductor, therefore we have a low-pass filter. Now we draw over here. Now we know that low frequencies go through the inductor. So that makes this high frequencies. Low frequencies go there, so the high frequencies get bypassed. That makes this a high-pass filter. So again, capacitor in series with the signal, high pass. Capacitor across the signal, low pass. Inductor in series with the signal, low pass. Inductor across the signal, high pass. So there's our RC filters and our RL filters, the 4 different types of filters and how they would be drawn. Once again, let's look at the formula for the inductive filter, the RL filter. So we know that at the cutoff frequency that our resistance is going to equal the inductive reactance. So inductive reactance is 2 pi FL. And if we apply a little algebra to that, we know we can take this R out and swap in the F over here. But then the R has to go on top. So our cutoff frequency is equal to R over 2 pi L. So now we've looked at low pass and high pass filters. Now let's look at band pass and band reject filters. And the simplest of these are simply made with resonant circuits. So if we have a series resonant circuit, how is that going to react? Well, let's put our source over here and have that go through a series resonant circuit. And what do we know? We know that this particular circuit, if I draw the graph here again, we know it's going to have a high impedance at high frequencies and a high impedance at low frequencies, but somewhere in the middle it's going to have a low impedance. So the curve is going to go something like this. That's the impedance curve. So at a particular frequency, this is going to look like essentially a short circuit. So let's flip this over. That's the impedance, and of course the impedance will be the inverse of the voltage that gets through. So what we're going to see, what gets through here, the signal that gets through, is going to look something like this. So at the resonant frequency, it's going to look like a short circuit, so the signal goes right through the second circuit and develops a high voltage. But below that frequency, not much gets through, so it doesn't develop much voltage. And vice versa, at higher frequencies, not much gets through, so it doesn't develop much voltage. I just want to redraw that as a load here, just to remind us that this is all working, that our circuit acts like a resistor. So if we get a lot of current, we get a a lot of voltage. So we get a lot of current at the resonant frequency, so we get a lot of voltage. But below the resonant frequency, we get less current, therefore less voltage. Above the resonant frequency, we get less current, therefore less voltage. So below the resonant frequency, goes up to the resonant frequency, we get our peak voltage, and then back down. So we see that we have a certain band of frequencies. What band? Well, what determines that frequency? It's going to be the resonant frequency. So our resonant frequency equals 1 over 2 pi times the square root of LC. We talked about that before, so I don't need to go into that now. And how broad is this filter going to be? Well, if we have some resistance in there, then that's going to pull that down, as I talked about before. As we add resistance to the circuit, we're going to pull down that peak and broaden the response of the circuit. So a high Q circuit, remember the Q comes from quality, the less resistance, the higher quality, so we get more of a peak. So we get a narrow band of filters. Remember, our range is going to be determined by where we get to that 3 dB point, that half power point, and that's going to be pretty near the top. So with a high Q, we're going to get a small range, but with a low Q, it's going to broaden that. So there is a filter that passes a band of frequencies, so this is going to be a band pass filter. Now what happens if we change that to a parallel circuit? Okay, now a parallel circuit does just the opposite. It's going to have a high impedance at the resonant frequency, but above and below the resonant frequency, we're going to get a low impedance. So it's going to act just the opposite. So that's a low impedance at the lower frequency, so we get a lot of current. Therefore, we get a lot of voltage here. So there is low frequencies, but it's going to dip down. At the resonant frequency, this looks like an open circuit, remember? Go back and look at parallel resonant circuits. So it looks like an open circuit, so not much current. Therefore, not much voltage, little current, little voltage. But below the resonant frequency, we get more current. Above the resonant frequency, we get more current. Therefore, below and above the resonant frequency, we get a high voltage through. But at the resonant frequency, the current is blocked. Therefore, we get a low voltage. So this makes a band reject filter. So if we put a parallel circuit in series with the signal, we get a band reject. But if we put a series resonant circuit in series with the signal, we get a band pass filter. And now let's put them in parallel and see what we get. So let's put a series resonant circuit here. So what happens? At the resonant frequency, we get a high current. Therefore, what do we get? If the current is going here, it's not going there. So at the resonant frequency, we get a low voltage here. So if we had the series circuit in series with the signal, we had a band pass filter. But now that short circuit goes this way. So at the resonant frequency, it acts like a short circuit. So we get less current through here. So we flip that around, we get a band reject filter. Now let's make this a parallel circuit. Now at the resonant frequency, this acts like a high impedance. So at the resonant frequency, we don't get the bypass, so our current goes this way. So then we get a curve that looks like that. So remember, at the resonant frequency, this looks like an open circuit. So if this is an open circuit, the current goes through here and develops a high voltage. There it is. Below the resonant frequency, this acts like a short circuit or a low impedance. So we don't get much current going through here, don't get much voltage. Above the resonant frequency, same thing. Above the resonant frequency, we get a lot of current through here. Therefore, less goes this way, and we don't get as much voltage. So let's take a look at the 4 configurations of our resonant circuits. So here's a series resonant circuit. Let's put our load over here. So what do we have? At the resonant frequency, we get a short circuit here. Therefore, it's a band pass. So low frequencies, not much current. High frequencies, not much current. The resonant frequency, lots of current. So it's a band pass filter. Now let's do the same thing. This time let's put the series circuit across the signal. So at the resonant frequency, our current tends to be shunted away. So instead of getting our current to go through at the resonant frequency, it gets shunted away. So now we have a band reject. Now we do the same thing here. Let's see, we did series circuits. Let's do parallel circuits. There's our load or our next circuit there. So now a parallel circuit that's going to have a high impedance at the resonant frequency. So at the resonant frequency, we don't get much going through here, so no voltage. But above and below the resonant frequency, we get plenty of current. Therefore, so at the resonant frequency, the current is blocked. So that's going to be a band reject. I think it's proper to have a hyphen in there. So remember, at the resonant frequency, this is a high impedance, so it's blocked, so it's a band reject. And last but not least, now what's going to happen at the resonant frequency here? The resonant frequency, this acts like a high impedance, so at the resonant frequency, the current goes through there, so that becomes a band pass. So there is our basic resonant circuit filters. So once again, at the resonant frequency, current goes through a series circuit. So this is a band pass. Near the resonant frequency, it passes the current. Across here, at the resonant frequency, the current goes through. It's a low impedance, so current goes through, current goes through. So if the current's going through here, it's not going through there, so it's a band reject. Here we have the same thing. At the resonant frequency, this blocks current, so that blocks a band of frequencies. Here at the resonant frequency, this acts like an open circuit. So at the resonant frequency, if the current is not going there, it must be going there. So that is a band pass filter. So there's our 4 iterations of resonant circuit filters. Now, another way we see filters is in some other configurations you should know about, because we often see them something more like this. So there is our, I'll just draw our source here again. Now these can act a little differently because of the design parameters. Well, we have 2 inductors. So basically it's a low pass filter because our high frequencies like to go through and be shunted away there, but they are blocked that way. So basically it's a low pass filter, but we use a different configuration. And what do you think we might call that kind of filter, since the configuration is, looks like Boba Fett's face, looks like a letter T. So we call that a T filter. And we can also make a T filter with capacitors. So we swap them around. I'm going to not draw the whole circuit. I'll just draw the components. So there is a low pass T filter, basically. And here comes a high pass T filter. So this would be a low pass filter, that would be a high pass filter. And these don't have as clean a characteristics. It's beyond the scope of this class at the moment to go into that, but we can create different types of filters with different characteristics when we start using the T configuration or variations thereof. And the same thing with the similar pi filter. I gave away the shape, didn't I? So we have our input over here, and let's do this with inductors. Well, with an inductor and two capacitors. So what is our shape here? Well, it's basically shaped like the Greek letter pi. So this is a pi filter. Now before we move on, let's not forget another type of filter which we're kind of forgetting about, because we can also do this. Low frequencies go through the inductor, high frequencies go through the capacitor, so this would be a high pass, and this would be a low pass. So that would be a L filter because of the shape. So these are simple filters. When we get to the pi and the T filters, we can tweak them a little bit to get different characteristics that, once again, I don't want to get into because that's beyond where I want to go at this point in the class. And as we make them more and more complicated, we can get more and more useful characteristics out of them. And of course, the next one I'm going to talk about here is going to be the final of this kind of filter that we're sort of looking at the moment. But we will see them occasionally. Can you guess what this filter is called? That would be an H filter. It's like a letter H turned on its side. So this would be an H filter. Once again, we can get more useful characteristics out of this by tweaking the parameters. And once again, I don't want to get into it at this point. So H filter, of course, could be either like that or like this. And we've already talked about tweaking the characteristics with resistance, so I'm not going to go into there at the moment. But let's take another look at something we might want to do with filters. Because so far we've looked at how we can tweak the response. We can have a filter with low resistance and get a very high Q, for nice steep sides and a narrow bandwidth. Or we can add some resistance and we can bring that down and get some more bandwidth. We don't have the steep sides. And this can be problematic if we need to have a sharp cutoff with a broad band. Because as you can see, if we broaden the band, we get less cutoff. We'll talk about this a little more when we talk about radio circuits, where this can be needed to be able to pick up a radio frequency and completely reject frequencies above and below. So how can we steepen that and broaden it out? So we can make a circuit that maybe looks something like this. Now we're getting complicated. Not going to talk too much about how to design such a filter, but we'll take a look at what we can do with such a filter. So there is our input, there's our output, there's the return or the ground. And so we have a series resonant filter this way. Oh, I didn't draw that quite the way I wanted to. That's better, not quite so weird. So we have parallel elements and series elements. So the series resonant circuit in series with the signal acts like a band pass filter, and the parallel resonant circuits across the signal also act like band pass filters. And this filter tends to isolate the other two, and so we can get a response where we get one filter does this, and the next filter does that, and the next filter does that. So we get three responses, and essentially we end up with a filter that does that. So we have a wide response. If we erase what's going on in here, let me get the eraser and do a cleaner job of that. So we can get a filter that has steep skirts and a wide bandwidth, should we need one. So that's our filter basics. Filters are a discipline all their own, so we don't want to go too deep into them at this point. But you might want to go over this video again and go over the reading material at Vocademy to make sure you understand the different types of filters, can remember your high pass filters from your low pass filters and your band pass filters.